In 7.2, we talked about infinite sequences. We talked about what they are, reviewed the idea of sequences and factorials, writing rules, and then we led into the idea of how a sequence is really similar in mannerisms to a function, and we can take limits to determine whether a sequence diverges or converges looking at limits. And what we're going to do in 7.3 is we're going to extend this idea to a series, which should take you a little bit back to your Algebra 2 and pre-calculus time where you analyzed series. And in those cases, they were typically finite series. So let's remind ourselves what a series is. A series is just the sum of the terms of a sequence. And in Algebra 2 and pre-calc, you focused on series that were finite. They had a starting point and an ending point, and you found the sum of those finite series. And you talked very briefly about infinite series only with respect to geometric. And we're going to focus a lot more on infinite series because, again, in calculus, that is what we really find interesting. What happens as we go to infinity? So we're really going to be focusing on, in all of these sections, an infinite series. So let's first quickly review the notation for series. You're going to see this giant sigma. It's going to tell you what value you are starting at, what value you are going until, and then it's going to give you your rule. So this is where you start pretty much every series. Actually, I think every series you're going to see is going to have an infinity above that sigma. So where you start, the n value you start at, to infinity, and then a sub n being your rule. What is that rule? So here you can see these are the first three terms. Over here, you're going to see the general term, which tells you what the pattern of the rule is. And important things to notice, I want you to see this notation where we include, in English, what we call an ellipses, the dot, dot, dot. So you're seeing a handful of terms, the first, the second, the third. Notice they're not separated by commas because this is a series. They are separated by plus signs or addition signs. Then in the middle, you see this plus dot, 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 plus the general rule showing you what that pattern actually is looking like. And then you see a plus dot, dot, dot. You have to have this notation with these plus signs and these ellipses. It's essential. Otherwise, you're not actually talking about something that is infinite. So just be really careful. I'm going to hit it hard that you see the notation and how you need to write things. So thinking back to 7.2, we talked about how a sequence could either converge or diverge, looking at what is happening for each of those terms. And we talked about this convergence and divergence by looking at limits. So for example, we looked at a sub n equals 1 over n, and we said what's happening to the terms? Well, if we start at 1, we have 1, then we have 1/2, then we have 1/3, 1/4, and each of those terms, we asked ourselves, is each of these terms converging towards a particular value? Meaning, is it heading toward a particular number? And in this case, we said, yes, this sequence does converge. All of these numbers are heading closer and closer and closer to 0. And we're going to use that same idea with a series now. We're going to be talking about not just each individual term, not what's happening with each individual term, but what's happening with the sum of these terms. Is that sum converging, meaning is it heading towards a particular sum value? Is it heading to a finite sum and converging? Or is it diverging? Is it growing without bound? Is it getting infinitely bigger? So I want you to go ahead and pause the video and quickly see, can you think of a series that diverges? A series that if you add the terms together over and over and over and over, that series is diverging. And then can you think of one that converges? Is it, as I continue to add each term together over and over and over, is that sum converging towards one value? So my first thought when I'm thinking about a divergent series is just the most basic series that I can think of, which would be that the sum from n equals 1 to infinity of n. So let's take a look at this sum. If I plug in 1, I get 1. If I plug in 2, I get 2, 3, 4, dot, 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 plus n, plus dot, dot, dot. This is growing to infinity. I'm adding 1, then I'm adding 2, then I'm adding 3. This sum is growing without bound. There is no value that this sum is converging toward. Now, let's think of an example that is converging. So if we look at the sum from n equals 1 to infinity of, let's say, 1/2 to the power of n. What is this sum doing? Well, this is 1/2 plus 1/4 plus 1/8 plus ... plus 1 over 2 to the n plus ... And what's happening in this series, these are getting steadily smaller, and this series is actually converging to a value. Now, you should know I haven't proved this to you. It just appears I'm adding 1/2 plus 1/4 plus 1/8 as n is going to infinity. These fractions are getting smaller and smaller. They're getting infinitely smaller, meaning in theory it's almost, if you think about it like a limit, it's almost as if at some point I'm adding 0, 1 over infinity to this. So this is converging towards some sum. Now, we haven't proven that. We haven't talked about what you know. We haven't even said what can we figure out what the value is that it's converging to. Right now, what we're saying is behaviorally, it seems as though this sum is converging. And that leads us to this next idea of how can we tell? We're going to spend a lot of time in the next 2 units, Unit 7 and Unit 8, learning about different series tests to help us identify, does something converge or does it diverge? So you're going to learn a significant number of tests that are tools that you can use to determine, does a series converge or does it diverge? So I wanted to really get that idea of a divergent series, meaning it's growing without bound, and a convergent series, meaning that that sum is heading to some finite number as we go to infinity. And now we're going to walk through in the rest of today's lesson 2 tests that help us determine whether a series converges or diverges. Or I should say 2 tests that help us understand the behavior of what's happening in a particular case. Something important that I want to talk about before we learn our first test is that some of the tests we're going to learn test for divergence only, some of them test for convergence only, and some of them test for both. But it's really important for you to understand what type of test it is. So for example, the very first test that we're going to learn is the Nth Term Test for divergence, which is often abbreviated using NTT, which you are more than welcome to do. This test only tests for divergence, which means if you do this test and it doesn't work, you can't conclude that a series converges. You can conclude nothing. You can conclude that you then need to use a different test. So let's talk about what this test is, and then I'll come back to that idea of it doesn't guarantee the opposite is true, or the biconditional statement is not true. So this test says an infinite sum will diverge if the limit as n approaches infinity of a sub n is not equal to 0. So if I look at a series and I take the limit as n approaches infinity of that pattern or of that rule a sub n, and that value is not 0, I can instantly say that that series diverges. If I take the limit and it does actually equal 0, I can conclude nothing. I can conclude that I then need to use some other test to determine what is going on with this series. So again, this test does not always work. Sometimes you will do this test and then realize you have to do another test. And we're going to learn a lot of different tests. For me, this is the first one I always check, at least mentally, because it's really easy to take a limit in my head and figure out what's going on. And if the limit is not equal to 0, that's going to save me a lot of work before having to look at one of the other tests that we're going to learn. So let's look at this first practice problem number 1. The sum from n equals 1 to infinity of 2n over the quantity 3n plus 1. So what we're going to do is we're going to take the limit of the rule. So the limit as n approaches infinity of 2n over 3n plus 1. This is a pretty basic limit problem, right? So as n is going to infinity, what's happening here in this polynomial expression, this limit is going to be 2/3. And 2/3 is in fact not equal to 0. Therefore, this series diverges by NTT. And I am going to expect you to name the test that you're using when you are determining convergence or divergence. Why don't you go ahead and pause the video and work through numbers 2 and 3, taking the limit as n approaches infinity and determining, does it diverge, meaning is it equal to something that is not 0, or can we not determine as of this point? All right, on number 2, we do get that limit is equal to 0 since the numerator is growing more slowly than the denominator. Therefore, we cannot conclude anything. We cannot conclude if this diverges or converges. As of right now, we do not have a method that will allow us to determine this. Number 3, the limit as n approaches infinity of 4 minus 1 over n squared. Well, 1 over n squared is going to 0, so this limit is going to be 4, which is not equal to 0. Therefore, the series diverges by NTT. So again, to wrap up the nth term test, in order to do this, we take the limit as n approaches infinity of the series. If that is not equal to 0, then we can say it diverges by NTT. If that limit is equal to 0, we have to use another test. So let's go ahead and talk about another test. Let's talk about the geometric series test. So before we can talk about the test, we should recap what a geometric series is. And this is something that you spent a decent amount of time working on in Algebra 2 and pre-calculus. And actually, a geometric sequence even back all the way to Algebra 1. A geometric pattern is a pattern where you're multiplying by some common ratio. Therefore, a geometric series means that you're taking the sum of a rule in which you are just multiplying to get the next term in the rule. So for example, 2 to the n would be a geometric series. To get the next term, you multiply by 2. So that would be 2, 4, 8, 16, etc. Now, if I wanted that to be a series, it would become 2 plus 4, plus 8, plus 16, etc. So that idea of geometric meaning multiplying to get to the next term. In sigma notation, that's going to look like the series, or sigma, from n equals 0 or whatever starting value to infinity of some rule, and that rule is going to have an r value, a being the first term, r being the common ratio. And I should say a is only the first term if we're starting at n equals 0. However, that same idea holds. So you may remember from pre-calc and Algebra 2 that a geometric series can have a finite sum and converge under certain circumstances. We actually learned a formula way back when. It may look kind of familiar. The sum of the infinite series is a over 1 minus r, which is also right here. It is possible to find the sum of an infinite series. And again, you did this in Algebra 2 and in pre-calculus, only under certain circumstances. So let's talk about what those circumstances are. We need the limit as n approaches infinity of a sub n to equal 0 in order for this series to converge, just by the way that it's set up. And in order for that to be true, we need that ratio, or the absolute value of that ratio, to be less than 1. We call checking the ratio of a geometric series the geometric series test, or GST. So this is one you're going to be using under the condition that we actually do, in fact, have a geometric series. So again, the great thing about this test is it tells us either the series converges or diverges, as opposed to NTT, where sometimes we have to use another test if that test does not work. This test will always work in the case that we have a geometric series. So let's go ahead and look at some example problems. Example A, so it says determine if the sum converges, if so, find the sum. And example A says the series from n equals 0 to infinity of 5 times 1/4 to the power of n. So I need to identify the ratio. The absolute value of the ratio is 1/4. And 1/4 is less than 1. Therefore, this converges by GST. So that is the work that you're expected to show. In order to show that the conditions are met, you show that the absolute value of r, whatever that number is, so in this case 1/4, is less than 1, therefore it converges by GST, and you have to state the name. And these problems are asking us, okay, so if that's true, find the sum. So the sum is the first term, which means in this case, I'm going to plug in 0 to find the first term. If I plug in 0, I get 5 over 1 minus that ratio. Remember, you do not have to simplify. You're more than welcome to leave it exactly like this. However, if you did want to simplify, that would give you 20 over 3. All right, so for part B, let's first actually write this out using series notation. So this is going to be the sum from n equals 1 to infinity of what's happening. We're multiplying by 1/10. So 1 times 1/10 to the power of n minus 1. And I always double check to make sure that this works. My first term should be 1, so when I plug in 1, I should get 1. So it is geometric. The common ratio is 1/10. So the absolute value of r is 1/10. 1/10 is in fact less than 1. Therefore, the series converges by GST. So in the next part of these notes, problems 4 through 14, I really want you to pause the video and take time to work through each of those problems and identify if it converges, if it diverges, or if neither of these tests work, so we actually can't determine, then you can say cannot be determined for that particular problem. Then we'll go over each of those problems and we'll talk about the last two, which is just a cool extension on this idea of geometric series to repeating decimals. So go ahead and pause the video, work on problems 4 through 14, and then unpause the video and see how you did. So here's the first 3 questions. On number 4, that ratio, so it's geometric. The ratio is 2/3, which is less than 1. So the series converges by GST. And that sum, you can leave unsimplified, 10 over 1 minus 2/3, or you can simplify it to be 30. But remember, simplifying often puts you at risk for making a basic math mistake, so just be careful. Number 5, that absolute value of that ratio is 4/3, which is greater than 1. Therefore, the series diverges by GST. Again, you can conclude either as long as it's a geometric series. Number 6 is not geometric. So the only other test we have at our disposal as of right now is NTT. So if I take the limit as n approaches infinity of n factorial over 2n factorial plus 1, I get 1/2. So something I want you to notice is that it does not say 2n quantity factorial. It says 2 times n factorial. There is a difference there, which basically means as n goes to infinity, this is almost like a polynomial of the same degree. Therefore, that limit is going to be 1/2, which is not equal to 0, so it diverges by NTT. Go ahead and work on 7 through 9. Okay, on number 7, you can rewrite that. The square root of 2 to the negative n power is the same thing as 1 over root 2 all to the power of n, which then makes this geometric. R, or the absolute value of r, would then be 1 over root 2, which is less than 1. Therefore, this converges by GST, and you can see in purple the sum, and I'm not going to bother simplifying that. I'm not going to bother rationalizing the denominator. I'm going to leave it exactly like that so that I don't risk making any mistakes. On number 8, this is obviously not geometric, so we're going to use the only other theorem that we know that might help us here, the only other test, which is NTT. So the limit as n approaches infinity of n over sine of n, and then analyzing that limit, the numerator is n and the denominator is sine of n. The numerator is growing incredibly fast in comparison to the denominator, which is really just oscillating between -1 and 0. So you can think of that as a fast over slow situation, meaning that that limit is going to be infinite. And since infinity is not equal to 0, this is going to diverge by NTT. Now, number 9 is a little tricky. I think it's pretty clear that it's geometric, but trying to write it in a way in which you can identify what that ratio is a little bit more challenging. So I want to work through that with you. -3 to the n minus 1 power is the same thing as -3 to the -1st power times -3 to the nth power, right? Because based on algebra 1 properties of exponents, we would just add those two exponents together. So the reason that I'm doing this is because I want to be able to have something either to the power of n or to the power of n plus 1 or to the power of n minus 1. And for me, it just seems really natural to take out that -3 to the -1st power, which is just 1/3. -1/3. So out in front, I'm going to have -1/3. And inside, I'm going to have -3 over 4, now both to the power of n. So first question, does this geometric series converge or diverge. So the absolute value of r is going to be 3/4, and that's less than 1. Therefore, the series converges by GST. And then if we were actually going to find that sum, I'm just going to ignore number 12 here for a minute. If we were actually going to find that sum, the first term, so again, notice that we have to plug in 0. If I plug in 0, that first term is going to be -1/3 over 1 minus that common ratio, which this is going to become -1/3 divided by 7/4, so times 4 over 7. So this sum is going to be -4 over 21. Now I want to show you something kind of cool. Some of you may have looked at this original series. So the sum from n equals 0 to infinity of -3 to the n minus 1 over 4 to the n, and thought, well, instead of making both of them to the power of n, as I did up here, what if we made both of them to the power of n minus 1 and looked at it geometrically that way? So let's do that. If I wanted them both to be to the power of n minus 1, my -3 isn't going to change at all. What I need is to have 4 to the -1st power out here. Or I'm going to show you that a little bit differently. -3 to the n minus 1 over 4 times 4 to the n, right? This would give me what I'm looking for, which is both of those exponents being n minus 1. So what I can do is take this 4 in the denominator, or take 1/4 and factor it out, so that I have this new expression, or this new summation for this series, which, looking at this, the common ratio is the same, so it is going to converge by GST, but let's confirm for ourselves here that the sum is the same. This is the same series, I've just rewritten it slightly different. The first term now, if I plug in 0, I'm going to get 1/4 times -4/3, if I substitute 0 in here, over the same denominator, right? 1 minus -3/4 or 7/4. So the numerator is going to simplify to be -1/3. We're going to multiply by the reciprocal of the denominator, and that's going to give me the same, oops, I should write it correctly though. That's going to give me the same sum that I got using the other method. So if it's geometric, even if you're manipulating it slightly differently to make the exponent the same so that you can identify that ratio, the sum is going to be the same. Obviously, that means the convergence is going to be the same as well. So your brain may go a different way when you're trying to simplify and rewrite that summation, and that's okay as long as we have equivalent series. Okay, for 10 through 12, I'm going to suggest that you write it using sigma notation first, and 12 is incredibly challenging. I'm going to encourage you to see, is there a way that you could actually break that into 2 different series and then find the sum of those 2 series separately? So that one's incredibly tricky. I want you to think about that for a minute, pause the video, and then work through those 3 problems. All right, on number 10, that pattern is n squared plus 1. So we're going to have the sum from n equals 1 to infinity of n squared plus 1. That's not geometric, so I'm going to use NTT. The limit as n approaches infinity of n squared plus 1 is infinite. It's growing to infinity, which is not the same thing as 0. Therefore, it diverges by NTT. Number 11 is geometric. The first term is 3, but that pattern is that it's multiplying by -4/3, and there's 2 different ways you could write that geometrically, sort of shown below. Either way, the absolute value of that ratio is 4/3, which is greater than 1. Therefore, this series diverges by GST. Okay, number 12, if you got stuck, I have now sort of color-coded what I want you to see as 2 separate series. So if you look at this as the sum of 2 different series, what I'm going to call the red series and the blue series, see if you can write a series for each of those 2 portions, and then see what happens if you try and add them together. So my red series, the first term is 1/3, the second term is 1/27, 1 over 243, so my common ratio is 1/9. My first term is 1/3. In order for this, when I plug in 1, in order for that to become 1/3, I need this exponent to be to the power of n minus 1. So I have set this up correctly. Well, looking at this, the absolute value of r is 1/9, which is less than 1. Therefore, this converges by GST. And we can, in fact, find that sum. So the sum is going to be 1/3 over 1 minus 1/9, which is 3/8. Now I want you to do something similar with the blue series. So looking at the blue series, 2/9, 2/81, 2/729. So the numerator is staying the same, and the denominator is increasing by multiplying by 9. So our ratio is 1/9. There's a couple ways you could write this. You could write this as the first term being 2/9 and either using 0 somewhere to make sure that this actually works out to give you 2/9. I'm actually just going to write this as 2 times 1/9 to the n, because let's make sure if I plug in 1, I get 2/9, and that's the first term. So my way is successfully giving me the right terms. If I plug in 2, I get 2 times 1/81, so I get 2/81. I'm confirming that this does, in fact, represent this blue series that I see up here. So again, the absolute value of r is 1/9, which is less than 1. Therefore, this also converges by GST. Yes, you do have to look at both of these separately and show their convergence and conditions separately. So now I can find the sum, which is going to be the first term 2/9 divided by 1 minus 1/9, which is going to be 2/8. That means that the total sum, since these two series are being combined together, right? The red series is an infinite thing that we're adding together, an infinite number of terms that we're adding together and is converging to have a sum of 3/8. The blue series is an infinite sum that's converging to add together to be 2/8. So I can add those two things together to get the sum of those two series being added together, which will give me 5/8. Now, this was an incredibly tricky problem that you had to analyze in a lot of different ways, but sometimes just looking at a pattern like this, it will sort of indicate to you as you practice more that maybe it should be split up into two different types of series. Go ahead and pause the video and work on 13 and 14. Now, number 13 doesn't really look geometric, but what is sine of 100? It's some number. Some number being raised to the power of n is a geometric series. Sine of 100 is the absolute value of r. Sine of 100 is less than 1. Everything in the sine function is less than 1 unless we're actually at one of the values where sine is 1 or negative 1. Therefore, this converges by GST. So the sum is going to be sine of 100 over 1 minus sine of 100. And I would not type that into a calculator. I would leave it exactly like that. For number 14, this one's a little tricky trying to figure out how to make both of these exponents the same. So if I know I want to make them e to the n minus, or I want to make them both to the power of n minus 1, what I need to do is figure out, okay, well, if this is just e, that's not going to get me there. If this is e squared to the power of n minus 1, when I use properties of exponents, just as in Algebra 1, if I distribute here or I shower the power, that would give me e to the power of 2n minus 2, which is the same thing as e to the 2n and e to the negative second power. But that is not the same thing. It's supposed to just be 2n. So how do we resolve that? We multiply this by another e squared, right? Because these two would now add to be 0. So that's where this value is coming from here. And you may have to pause and rewind or just pause and really look at that for a minute to understand how that came to be. But it is important that you can use these Algebra 1 properties to manipulate this series to make it look the way that you need it to look. So now that we have rewritten it in that way, we can identify what r is for our geometric series. So the absolute value of r is going to be e squared over 6, which is greater than 1. Therefore, this diverges by GST. Let's go ahead and look at our last two examples, which are going to ask us to use a geometric series to find the fraction form of the repeated decimal. So what I want you to do is think about how could you rewrite 5.22 repeating? How could you rewrite that as a geometric series? So 5.22 repeating could be written as 5 plus 0.2 plus 0.02 plus 0.002, and that could continue on infinitely, right? That's what this is representing. So how could I rewrite this using sigma notation? Well, I could just write 5 plus the sum from n equals 1 to infinity of 0.2 times 1/10 to the power of n minus 1. You can pause the video and confirm for yourself that that does actually make sense, that that series is what we're talking about here. So looking at just the series, ignoring the 5 for a moment, this is geometric. The absolute value of r is 1/10, which is less than 1. Therefore, this converges by GST, which means we can find the sum. So that sum is going to be the first term, which is 0.2, divided by 1 minus that common ratio, and this is going to simplify to be 2/9. And if you're not seeing that, remember that 0.2 is 2/10. We're going to divide that by 9/10. That's going to just give me that 2/9. That's where that's coming from. So this series is really 5 plus 2/9, which if we just wrote that, 5 and 2/9, 47/9 is how we would write this as a fraction as opposed to a repeating decimal. So just kind of a cool way to extend this idea of series and geometric series specifically back to the idea of repeating decimal, something that you probably first learned about in 6th or 7th grade. I want you to try the last one on your own and then unpause the video and see how you did. And there you have the worked out solution to number 16. So recapping 7.3, the big ideas here. Applying what we learned about sequences to series, deciding if a series converges or diverges, and really the focus of this section was 2 specific tests. The Nth Term Test, NTT, which only tests for divergence. So if you take the limit as n approaches infinity of a sub n, and that is anything besides 0, you can say that that series diverges. You can never say that a series converges by NTT. It is a test solely for divergence. So if that limit is actually equal to 0, that's a way of telling you, or a spoiler alert, that you need to use a different test to evaluate whether that series converges or diverges. And the other test that we learned in this section was the geometric series test, which works for any geometric series. We went back to Algebra 2 and recalled how to find the sum of an infinite geometric series and when that applies, and that only applies when the absolute value of the ratio is less than 1. The geometric series test always gives you the answer of whether the series converges or diverges. If the absolute value of r is greater than 1, it diverges. If the absolute value of if the absolute value of r is less than 1, it converges. And then you can actually find that infinite sum using the formula that you originally learned in Algebra 2. Looking forward to supporting you on this in class. Thanks for listening.